Let C be a smooth curve with parameterization R of t, and let t be between A and B. F is a continuous vector field over a region containing C. The flow along the curve from A, I'm missing a word there, and this is where I should just restart this video, but I'm just going to, from A equals R of A to B, which is R of B, is, and here we see flow is a path integral through this vector field. So we start at A and go to B. We call this flow. And I guess the conversation to have is, what is this measuring? Well, the way I like to think about it is this is a velocity equivalence to what work tells us about force. When we calculate work, those end up with units that are force distances, right? We're talking about a force acting over a distance, and this is a velocity acting over a distance. And if I think about F dot t at any point here, right, there's a unit tangent direction and the projection of the vector. We're adding up all of the velocities acting over a little distance, ds. And so the units here would end up being velocity distances, right? And so if we were measuring velocity in meters per second and therefore measuring distance in meters, the units here would be meters per meter per second meters, right? And you'll hear people say square meters because we're talking about multiplying. So it'd be square meters per second. I like to think of it as meters per second meters because it's a velocity distance. It's velocity acting over a distance the same way work is a force acting over a distance. If we increase the size of the vectors in the vector field, particularly the amount pointing in the tangent direction, then there's more flow. Well, and consequently, if we have a longer path that moves right, if there's literally more length, the flow would also increase. But if I just look at the same length path and I increase the amount of this vector that's going in the tangential direction, more flow. Well, everything we know about these path integrals will still apply. In fact, all of the many, many different ways that we wrote down a path integral apply in this situation as well. And I'm only going to write two more down here. So f of r of t dot dr dt, and then where m, n, and p are the components of my vector field, those continuous scalar components of my vector field. And this one is going to be very helpful for us in our next video when we talk about flux. And flux is only defined in the plane, so if we were dealing with a plane curve, very much the way I've drawn here, I don't need this k component, and I would just be looking at m dx plus n dy and a line integral right there.